Length contraction is a strange phenomenon whereby it's hard for us to comprehend, us as individuals, what is actually going on that allows Mother Nature to make something seem like it's shorter than it is. And in fact, it is shorter in our frame of reference than it actually is in real life. So let's have a look at a situation. There's nothing quite like a scale drawing to demonstrate this. I don't expect you to understand, to be able to reproduce this. It's definitely not a situation that's examinable, but hopefully you come along the journey with me and I've explained this in a way that will show you how something has contracted in length. So here's a situation. Here's a rocket flying through space, and here is us. This is our eye. We're going to stay stationary, and the rocket is going to go forward, and its velocity is half the speed of light. So light is actually travelling twice the speed of the rocket. Again, another way of saying that is the rocket is travelling half the speed of light. So here's the rocket's starting position. Okay, and here's our eye. So it's obviously not to scale, but let's look at this scale drawing. And it's really important for us to understand that for us to see something and interpret its length, what we actually interpret is light received by our eyeball at the same time, in the same instance. And our brain interprets all the light it receives at that moment and makes an image and makes an interpretation and actually makes a measurement. So the way that this works is light has to be received by our eye at the same time for us to make a measurement of its length at that point in time. And this is where relativity and relativity effects, my apologies, are seen when you start to get to speeds that are comparable to the speed of light. Okay, so we're going to consider the light leaving the front of the spacecraft at this point in time. Okay, so we're going to call them the green dots, and we're going to use this piece of card here as our measure, as our sort of ruler, so to speak. So this is obviously going to be at light speed, and here's our first light ray leaving the front of the rocket and heading towards our eye. Okay, so this light ray is obviously travelling at the speed of light. So we've got 1, 2, 3, 4, 5, 6 of those dots. 6 of those periods, not dots, 6 of those periods to reach from the rocket to our eyeball. Now, we're going to consider the ship's movement now. Now, the ship is moving at half the speed of light. So in one of these time intervals, it's going to go half as far. So we're going to use half a card length for the ship's movement and 6 of those intervals. Okay, so in that period of time, the ship has moved this far. So by the time the light ray that left the front of the rocket has actually reached our eyeball, okay, that one there, this light ray here, I'm going to circle it with white, actually comprehends with this one, coincides in time, in real time with this. So the front of the spacecraft is actually here now. So the weird thing is we actually have to do the same thing to the back of the spacecraft because it's a fixed object. So we're going to do the same thing to the back. This is actually attached to the rocket. Okay, so what we've got now are 2 points that are exactly the same length as the original rocket. So when this green light ray reaches our eye, this green one here, and I'll put it as a line now so you can see it. Okay, what has happened is that the spacecraft has moved forward this much. So let's draw as our new spacecraft now. Let's call it yellow. Okay, and our spacecraft is actually here now. When the green light ray hits our eye. Now, because the speed of light is constant in all frames of reference, we need to find a point where the light ray that left the front of the rocket actually goes past the back of the rocket at that point in time. So we need to actually start to match these up. So this one here matches this one here. So clearly they don't align, because if a light ray leaves the back of the rocket here, it's going to beat it to our eyeball than the one at the front. Okay, so let's just move 2 forward, okay, and that one matches that one, and that one matches that one. So clearly, it's actually going to be somewhere around here. And then what's going to happen is that this light ray is going to leave the back of the rocket from about here. That's our first circle. And then it's going to travel along at the same speed as the light ray that left the front. If that's where the back of the rocket ship was at that point in time, we draw a line there, and then if we colour in the part of the rocket that our eyeball sees at that point in time, you can see that L is less than L naught, where this length here is L naught. So this is, if you're on the rocket, you'd measure it to be this length, but if you are on Earth looking at the rocket go away from you, it has been contracted. Again, I don't expect you to be able to replicate that, but that is the explanation using rays of light as to why things actually do contract. They don't just appear to contract. Because you make a measurement, it is actually contracted in your frame of reference. Again, strange, but don't forget your frame of reference is different to that of the rockets, so it actually makes no effect to anyone on or in the rocket itself as to how you are perceived. And that's relativity, that's length contraction.